This is part 2 of the Operational Amplifier Differential Amplifier video series. In part 3, we'll be utilising the equipment again, and we'll be using AC in conjunction with the board. But today, in part 2, we'll have a look at some calculations. Common mode lab and common mode rejection ratio, part 2 of 4. Calculating the AV differential and the AV common mode. This lovely board we have to work on has LM394, a balanced pair of transistors, which helps a lot in this type of situation. If I was just to take 2 transistors off the shelf with beta variations, I wouldn't be able to get anywhere near the merit figures that I'm going to get today in the lab. We're using the Rigol oscilloscope. We're looking at the output from channel 1, or the LM394 Q1, and looking at the output of Q2. We have 2 inputs. The inputs, for convenience and to make the CMRR part work better in this lab, I've used 2 series resistors to isolate base currents from each other and fed them to the same signal generator. I'm using 250 Hertz, and I have to set this for an amplitude which does not overdrive each of the transistors. These transistors do have quite a bit of gain in this configuration, so it turned out that I only needed about 30 or 40 millivolts coming into the base of each transistor. In part 1, we'll be using the 22K long tail resistor. That's this one here. This is the constant current source. We'll be looking more at this in video number 3. However, we will be using it today in the calculations to see what impact it has on the CMRR quality. So in part 1 we use 22K long tail resistor. By using the same output on a common mode signal generator, we can be sure to have the same amplitude and frequency at the inputs with no phase difference. And that's very important. In the very last slide here, I'll discuss that phase difference and the tiny voltage amplitude difference that would really screw this common mode rejection ratio up. Differential gain using a single-ended input. Well, using a single-ended input here, I've highlighted this with an orange square around this side of the board, and I'm only using the audio coming into Q1. I'm not connecting the bass on Q2. So then I'll have an audio voltage at the collector, audio voltage I can measure on the bass, and I've gone ahead and done that. I got 39.8 millivolts RMS on the bass. That was with no distortion, as I said earlier. The voltage on the collector was 983 millivolts RMS. That gave me a 24.7 times gain. The AV differential then was 27.8 dB, i.e. that's 20 times the logarithm of brackets VO divided by VN, output voltage divided by the input voltage. So we've got quite a bit of gain in this little circuit. The common mode gain, and now we're looking at double-ended. So double-ended, I'm going to connect up the other base to the same signal generator, but again using isolation resistors between the bases. And in the common mode gain, first of all we'll do it with a 22K long tail, and then second we'll do it with a constant current source. So in scenario number 1, it turned out that I got minus 16.9 dB of common mode gain, and let's see how that happened. Number 1, I got 39 millivolts in. Now that's a little bit different to the 39.8 I had earlier. That's because now I've got the input going to 2 bases. Even I've got isolation resistors there. It did drop the output just a little bit. I measured 6.2 millivolts out at the collector of Q1. 6.2 V out divided by VN, 0.159 times gain. To get the AVCM in decibels, 20 log of that value to give me minus 16.9 dBs. There it was there. Scenario number 2, constant current source. Constant current source, I have a switch on the board. I switched from long tail 22K resistor across to constant current source, which effectively gives me a very, very high resistance at this point here, allowing for any small variations in the emitter from one transistor to be passed across to the other transistor perfectly with no loss. So we would expect to get a better ratio here, and in fact we did. We got minus 20.2 dB. Let's look at the figures. Now I measured only 3.8 millivolts out, and again that's going to be at the output of Q1 and using the inputs going into both of these transistors. Ideally the output at the collector of Q2 would have been the same because they are a differential pair. 3.8 millivolts out, 39 millivolts in, 3.8 divided by 39, V out divided by Vn, 0.0974 times gain. So the AV common mode, the voltage gain common mode, 20 log times this value minus 20.22, and that's the value that I've got there. Working out the common mode rejection ratio, and this is what we see with all operational amplifiers, of course, and they are much, much higher than what I get today. Case 1, case 2, we have to do the AV differential, and I've just worked in ratios here. AV common mode, 20 log times that again. So in case 1, we had 43.8 dB, that's with the 22K. Case 2, constant current source, 48 dB of common mode rejection ratio. So in part 2, we'd certainly see a significant advantage with using the constant current source. That's an extra 4 dB of rejection that was obtained. We use the left-hand side again of the differential pair for the single-ended difference signal. Only one base has the input in this case. Probably I'd meant to put that at the very beginning of this, and I sort of just squeezed it in down there on the day. Here we go now. Look, I'm going to be using in part 3 of this video series a transformer, a one-to-one transformer from the that I'll be putting across the collectors and then putting that into an audio amplifier, so that using 2 discrete signal generators and hoping that I've got exactly the right voltage peak to peak and exactly the same frequency and phase, I can get some balance happening here. Any imbalance that we get, we'll hear that in the way of an audio signal coming out of our amplifier, because I'll have an imbalanced situation set up between the 2 collectors. Now, why is common mode rejection ratio so important? Here's a Behringer ECM8000 schematic diagram. The schematic diagram did have a small fault with it, I found. I had to erase this section and put this capacitor up to the emitter on the BC118, because this is in fact a phase splitter. This uses 48 volts phantom power, but I will note it uses also an electret condenser microphone cartridge. Does not need 56 volts of bias like we normally see in condenser microphones. This stays permanently charged throughout the life of the microphone. We have a 2SK series FET happening here, then a BC118 phase splitting the signal. Then we have a balanced voltage extraction system here. 48 volts appears in the center, which goes across a 47 microfarad cappy. 5.6K series resistor down to a 6 volt Zener and down to ground. All of this part of the circuit here is supplied by the 6 volt rail, which now exists along the top. These act as emitter followers, so I have a voltage represented by this phase. I have a 180 degree phase difference here. Both of those voltages reappear again at the emitters, which go along XLR2 and XLR3 cables all the way back down, maybe a 50-meter run, who knows, all the way back down to our preamplifier or mixer circuit, where we have the 48 volts phantom power, which is split by 2 lots of 6.8K resistors. The 48 volts rides up to the microphone to power the microphone. The signal rides back along the top of the 48 volts going back into the preamplifier. Very, very common method of supplying the power to, called phantom power, to condenser microphone circuits. If that was not an electret condenser in this particular microphone, there would be a voltage inverter built into this, a low noise voltage inverter, and that would step up the 48 volts to 56 volts, and that supplies the cartridge, the condenser cartridge in the microphone unit. And there's just another picture there showing the actual XLR connector, and again the fact that pin 1 is ground and pin 2 and pin 3 carry a differential signal to the microphone preamp from the microphone itself. And here the beauty is, of course, hum. Hum is a big problem in audio circuits. This is a shielded cable, but hum will always find its way in from 50 Hertz or 60 Hertz power line signal. Any hum will be common in both the red and the orange wires, that is XLR2 and XLR3. And because the hum is going to be identical value and identical phase, identical signal level and identical phase in each of those wires, the common mode rejection ratio in the preamp will eliminate the hum. And that's what we've been talking about, because this preamplifier here is going to always be starting off, whether it's an operational amplifier or whether it's done with discrete components, it's going to be done as a differential pair. And the beauty is that we then can have our differential amplification factor and our common mode, very low hopefully, amplification factor, and therefore we eliminate the hum and we only amplify the good part. Now, before we finish this video, one more little thing to have a quick look at. Here's a differential amplifier that I've built using iCircuit, and this is a bit of a funny differential amplifier because no one would build one like this. I've made a series of 4 different differential amplifiers that again we'll have a better look at in video number 3. This particular one uses only one rail voltage, and it's set up as a voltage divider bias. Because it is a voltage divider bias, I have to use isolation capacitors going to my signal generators. I'm using 2 signal generators. I have 10 microfarad isolation capacitors. I have a 180 ohm common emitter resistor which is shared between both of the emitters. And at the moment I have 50 millivolts at 20 Hertz in the right hand. I have 20 Hertz at 50 millivolts in the left hand side. And when I activate this differential amplifier, you can see here yellow is the output from my transformer. Yes, I have a transformer going across both collectors, and I've got no signal at the transformer. I'll pause this so that we can get a better look at some signals. On the collector of Q1, that's red, it's going positive, and at the same time in green, the collector on Q2 is going positive. So Q1 collector, Q2 collector are both going positive at the same time. Likewise, they both go negative at the same time. The signals are in phase and the signals cancel out perfectly. Between each collector and ground, of course, we get a signal, but across the 2 collectors, we don't get any signal, and that's why the yellow was a flat line event. Now, what I'm going to do, I'm going to start this simulator again, and I'll go in and I'll change one of these signal generators. I'll make this 50.1 millivolts. Now look what's happened. I'll pause it. Now I've got an output situation on the yellow because now I have a difference between the Q1 collector and the Q2 collector. Only a tiny difference, only, what's that, 0.1 of a millivolt. That's 100 microvolts of difference that I've got between the 2 signals. It's more than enough to upset the balance in this differential amplifier now and give me an output situation between the 2 collectors. We'll have a closer look at some more circuits in video number 3, and we'll also go to the bench and use the live equipment to demonstrate all of these things that I've shown and talked about here in video number 2. So, this has been Greg Moore for TAFE New South Wales, introducing the operational amplifier differential pair. Thank you very much.